Welcome to Luvitex Engineering, where we sketch out the things that keep the industrial world moving. Now, let's start.
Today we're exploring a world that is totally ubiquitous yet entirely invisible to most of us. We're talking about solenoid valves. You might not realize it, but your entire day, literally, is dependent on these tiny hidden gatekeepers working behind the scenes from the second you wake up until you go to sleep. So think about this for a second. How do machines actually control the flow of fluids? I mean, how does a computer tell a physical liquid or a rushing gas to stop, go, or change direction? We're talking about everything here, from the water rushing into your dishwasher to the exact tiny droplets in an inkjet printer, even life-saving medical devices like oxygen concentrators. Or get this, the propulsion systems on satellites orbiting the Earth right now. How does that actually work? Okay, let's dive into this. Here is our roadmap for today. 1. Meet the solenoid valve. 2. Anatomy of a valve. 3. Valve types and configurations. 4. Rules of valve selection. And finally, 5. Preventing coil burnout. Section 1. Meet the solenoid valve, the everyday hero. By definition, a solenoid valve is an electromechanical device used to control the flow of a liquid or gas. Now, the absolute magic word here is electromechanical. These devices basically act as translators. They take an electrical signal from a computer or a switch, the digital world, and they convert it into actual physical mechanical movement to control a fluid. They are literally the bridge between digital brains and physical plumbing. Now, what's really interesting here is this stark contrast in the hardware. If you look at the bottom, you've got that heavy-duty brass body with threaded pipe connections. That's the fluid plumbing part. But bolted right on top of it is that green plastic encased box with the red wires. That right there is the electrical brain, the coil. And these little gatekeepers, they basically juggle 4 main jobs. The simplest one, just opening and closing. Think of your dishwasher snapping shut to conserve water. Second, they act kind of like traffic cops, controlling flow direction to mix fluids together. Third, they manage volume. That's how they dispense those exact microdroplets in your inkjet printer. And finally, they regulate flow rate, meaning they can pulse rapidly to carefully meter out life-saving gas in something like an oxygen concentrator. Pretty versatile, right? Let's move on to Section 2, Anatomy of a Valve, breaking down the magic. Looking a bit closer at the valve itself, we can really start to appreciate the separation of concerns going on here. That green box on top houses a coil of insulated copper wire. And below that, safely tucked inside the brass body, is an orifice, which is just a small hole where the fluid passes through, and a seal. But here is the really fascinating part. The electrical wiring never ever touches the fluid. The connection between the electrical half and the plumbing half is entirely magnetic. Let's move to and see how this builds into an exact sequence. It's like a chain reaction. Step 1, an electrical current is applied to that copper coil. Step 2, this immediately forms a really powerful electromagnetic field right in the center. Step 3, that magnetic field physically pulls a soft iron plunger in a straight line. And step 4, as that plunger moves, it lifts a seal, which instantly allows or blocks the flow of the fluid. Boom, it's that fast. Section 3, valve types and configurations, understanding the variations. So, because applications vary so wildly, the most fundamental variation you'll see in these valves is their resting state. A normally closed valve, or NC, uses a spring to firmly block the flow of fluid until you power it up. Conversely, a normally open valve allows fluid to flow freely when there's absolutely zero power. It only actually shuts off when you apply an electrical current. Engineers have to choose these based on a really critical question. What needs to happen if the power suddenly goes out? Like, if you lose power, do you want your fuel line to stay wide open, or do you want it to snap safely closed? Another really vital comparison is direct-acting versus pilot-operated valves. Direct-acting valves rely 100% on the brute force of the magnetic coil to fight against the fluid pressure and open that seal, which is great, for low-pressure systems. But for high-pressure systems with massive amounts of fluid flow, the coil just isn't strong enough on its own. But it turns out there's a really clever workaround for this: pilot-operated valves. These use a tiny direct-acting solenoid as a sort of pilot to slightly shift the internal pressure balance, so they actually use the rushing fluid's own power to help force the main valve open. It's kind of like using the fluid's momentum against itself. Section 4. Rules of valve selection. Choosing the right gatekeeper. Now, selecting a valve isn't just grabbing one off a shelf. It's a high-stakes checklist. First up, operating pressure.
The valve absolutely has to overcome the system's maximum opening pressure differential, or MOPD. If it can't, the magnet just won't be strong enough to open it. Next, media conditions. Are you pumping regular cold water or are you pumping a highly corrosive acid? The seals have to perfectly match whatever is flowing through. Ambient conditions matter too, for sure. I mean, an underwater valve is going to need a watertight IP67 enclosure to survive. And finally, coil voltage. Give it the wrong power supply and the valve will either just sit there, staying shut, or it'll severely damage itself. Miss even one of these limits and your whole system fails.
Which brings us to Section 5, Preventing Coil Burnout, Troubleshooting the Failure Point. So the crucial point here is a massive 5x multiplier. Let me explain. When an alternating current coil, an AC coil, is first turned on, it experiences this initial surge of electricity called inrush current. This surge can be up to 5 times higher than its normal, everyday operating draw. And the crazy thing is, it stays dangerously high until the magnetic plunger finishes moving and totally closes the air gap inside. Knowing about that massive inrush current totally explains why these coils burn out. Just think about undervoltage, right? If the magnetic field is too weak to fully pull the plunger all the way in, the valve continuously draws that massive 5x surge until the insulation inside literally melts. The exact same disaster happens if even a tiny piece of dirt jams the plunger so it can't seat fully. Add in things like rapid cycling, which builds up trapped heat with no time to dissipate, or electrical spikes from nearby heavy machinery frying the insulation, and you can easily see why these normally robust components end up failing. And this brilliantly illustrates the real engineering trade-offs between AC and DC coils. AC coils are incredibly fast, but they are highly prone to that fiery inrush burnout we just talked about. DC coils, on the other hand, have a steady, consistent current. This makes them highly resistant to burnout and really great for rapid cycling. But there's always a catch, right? DC coils store energy that can shoot a damaging electrical arc right across your switches when they're turned off. So if you use DC, you have to specifically wire in an extra component to absorb that hit. As we wrap up this explainer, I want to leave you with a bit of a provocative thought. Right now, as you sit there, how many solenoid valves are silently working all around you? I mean, think about it. In your heating system, your refrigerator, your car, your local water supply, they really are the ultimate invisible workhorses, bridging the digital and physical worlds. So what would happen if they all simply stopped translating electricity into motion at the exact same time?
Thanks for watching. For more industrial insights, check out our other videos. Don't forget to like, share, and subscribe to Luvitex Engineering.